In this video, we'll be covering section 5.8, matrix inverses. We have two objectives. The first one is to just find the inverse of a matrix, and then the second one is to use inverses of matrices to solve systems of equations. Before we can find the inverse of a matrix, though, we need to set up some terminology. The first term is identity element. We have used this term, or used the idea of an identity element, all the way back from elementary school. We know that if you take any number and you add 0 to it, you get the original number back. This is what it means to be an identity element. When you take that number, in this case 0, and you perform an operation with any other element from the set, it doesn't change the identity of that original element. And it doesn't matter which order you add here. The commutative property says that 0 plus a is always going to be a, or a plus 0 is a. We see a similar relationship with the number 1 and the operation of multiplication. If you take a times 1, you just get a. If you take 1 times a, you still get a. So it has the same algebraic property as 0 has with respect to addition. So in general, we say that an element E is an identity element of a binary operation. In this case, I'm just calling the binary operation star. Could be any type of binary operation. If A star E is equal to E star A equals A, meaning that applying the operation with this E element does not change the original identity of the other number or element that we're dealing with. This concept can be extended to all sorts of binary operations. So in particular, we want to apply it to matrix multiplication. Okay, so what we're looking at is we want to find a matrix that has the same property as the number 0 does with respect to addition and as 1 does with respect to regular multiplication. We're going to call that matrix the identity matrix, and so it should have a similar type of relationship, meaning that take a matrix A, multiply it by the identity matrix, it should give you the matrix A back. Similarly, the identity matrix multiplied by that matrix A should give you the identity, or give you the matrix A back again. Now, matrix multiplication has some unique properties that is going to kind of restrict the type of matrices that we could come up with for an identity. So what do I mean by that? Well, remember, for matrix multiplication to be defined, they have to have the correct dimensions. Let's say that matrix A is an M by N matrix. And let's say that matrix I, well, in order for that product to exist, it would have to be an N by P matrix. These two have to match each other. The number of columns has to equal the number of rows for that second matrix. But we're saying that this product also has to exist. So that would be an N by P multiplied by an M by N. Well, that forces these two dimensions to match, but the product that you would get here would be an N by N matrix. And that product has to be the same as matrix A then. Right? We're saying they're equal. So what this is getting at is the identity matrix will have to be a square matrix, and it will have to have the same dimension as the matrix A, which means matrix A has to be square as well. So we can have an identity matrix for any given square matrix, so whether it's 2 by 2, 3 by 3, 4 by 4, or 25 by 25. So let's look at the identity matrix for just 2 by 2s first. We've seen this matrix before. It's just a 1s across the diagonals and 0s everywhere else. So we're going to denote that as I sub 2, the 2 by 2 identity matrix. Now, before you take my word for it, let's actually verify that it is indeed an identity matrix. So we're going to start with a general 2 by 2 matrix, could represent anything. And what we need to show is that A multiplied by the 2 by 2 identity matrix does actually give us A. That's what we have to verify here. So remember, the way matrix multiplication works is you take a row and you multiply it by a column, and that's going to give us this first element here. So x times 1 plus y times 0, that's where this is coming from. If you simplify that, you can clearly see you just get x in that first element. Okay, then you go back and do the same process, rows by columns. So this row by this column, x times 0 plus y times 1 gives you this, and that simplifies down to y. To get the second row over here, you take the second row by the first column to get this element here. So z times 1 plus w times 0. which just gives us z, and then this row times this column, so z times 0 plus w times 1 just gives us the w in that spot there. So you can see, after you do all this simplifying, yes, the matrix A times the 2 by 2 identity matrix does just give you matrix A back. All right, I won't torture you with the second one. I'll let you work through that yourself, but you can see here that the 2 by 2 identity matrix times A, by switching them around, does give you the same thing. Remember, with matrix multiplication, it is not commutative in general. A times B does not have to equal B times A. So that's why we are checking both of these. This leads us to the general definition of an identity matrix, the n by n identity matrix, which is consistent with what we said before. It's just going to be a square matrix of dimension n by n, where ones are along the diagonal and zeros everywhere else. So let's try that with a 3 by 3. So here's a matrix A. I want to write down the 3 by 3 identity matrix and show that A times that 3 by 3 identity matrix is actually A. So the 3 by 3 identity matrix is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Ones on the diagonals, 0 everywhere else. And we want to then verify that A multiplied by the 3 by 3 identity matrix, which would be this big thing, multiplied by the identity matrix, gives us actually A again. So let's go through the math here. So to get the first element, we take this row and multiply it by this column. And you can see if I take all of these numbers and multiply down this column, the only thing that's going to survive is the negative 2 times that 1. So negative 2 there. It'd be plus 4 times 0, plus 0 times 0, but that's not going to contribute anything. To get this next element, you take, again, the first row by the second column. Again, it's mostly zeros. The negative 2 gets canceled. This 0 is going to cancel that 0, but the 4 times the 1 survives, so you just get a 4 there. To move on to the third element in the first row, it's the first column by the, first row by the third column here. So again, negative 2 times 0 is going to get wiped out. 4 times 0 gets wiped out. 0 times 1 gets wiped out. Only thing you get there is 0. Now we move on to the next row. So it's second row by first column, and you can see the only thing that survives there is the 3 times the 1. 5 times 0 is going to cancel. 9 times 0 cancels, so we just get 3. And we just keep doing this, and you can see each time you are just going to get the corresponding element back from this first matrix. This row by this column, you just get 5. This row by this column, you just get 9 times 1, and that completes the second row. Third row, take that row times the first column, and you have 0 times 1, 8 times 0, negative 6 times 0, they all get wiped out, you just get a 0 there. Third row times second column, the only thing that survives is 8 times 1. And then third row times third column, the only thing that survives there is the negative 6 times the 1. And there you have it. Again, it is just the same matrix back. Okay, so we've defined what the identity matrix is, and this leads us to the concept of an inverse. So the idea with an inverse is that, in particular a multiplicative inverse, is that if you have two numbers that multiply together to give you the identity, then that means they are inverses of each other. B is the multiplicative inverse of A because their product is the identity element, at least in this case with respect to multiplication. Now, when it's just regular numbers, we know exactly what B has to look like. B would have to be the reciprocal of A. A times 1 over A is 1. And obviously we can flip those around in the other direction as well. So this tells us that the multiplicative inverse of A is just 1 over A. Now, if you recall from earlier in the year, we defined 1 over A to be equal to A to the negative 1, right? That's how we defined this negative exponent. So they are actually the same thing. So in other words, we could write this equation as A times A to the negative 1 also is just 1. Now, we are going to steal this notation for matrices. we want the same concept. We want to find two matrices whose product is the identity matrix. And the matrix that you get here will be defined to be the inverse matrix. And so we use this same negative exponent here just to indicate inverse. We see the same thing with function notation. The inverse of a function, we put a -1 exponent. But remember, we are not using the algebraic definition. It does not mean 1 over f of x. Similarly, for matrices, the inverse of a matrix does not mean 1 over the matrix. Okay, unfortunately, it's just not that simple. But it is using the same concept, so this means inverse here. Okay, let's start off with just the 2 by 2 case. So our goal is to find, if I give you a matrix, I want to find the inverse of that matrix. We don't know what it is, so I'm just going to put variables in for its components, x, z, y, and w. And so we are assuming that this is actually the inverse. In other words, we're assuming that if you multiply these two, you would get the identity matrix. So I've written that out here. This is A times A inverse, and I'm assuming you get the identity matrix, the 2 by 2 identity matrix here. So if we actually do the multiplication, again, rows by columns, so first row by first column, 2 times x plus 4 times z. That's where this blue expression comes from. Then we move on to get this expression. It's still first row, but by second column, 2 times y plus 4 times w. That's where the green comes from. Moving on to the second row, we take the second row by the first column, 1 times x minus 1 plus 1 negative 1 times z would just give us x minus z. And then this final element would be this second row by the second column, 1 times y minus w in that case. So this product, we're saying, is really A times A inverse, so it has to be equal to the identity matrix. These two matrices have to be equal. Well, we could represent this as a system of equations. This expression has to be 1, this expression would have to be 0, this would have to be 0, and this would have to be 1. So I've just rewritten that here. Right? We're saying these two matrices are equal, which means their components have to be equal. Notice that the first two equations I have here, which correspond to these two, are both in terms of x and z, whereas these two equations are in terms of y and w, which means you could actually write these back in matrix form. This is a system of equations. It could be written as this augmented matrix here. Similarly, this one could be written as this augmented matrix. Now, even though they have different variables, notice that their coefficients are exactly the same. So the coefficient matrix that you see on each of them completely matches. It's just the solution part over here that is different. Now, if you think about, we need to solve these systems. We could just go through and do it by hand, do elimination or substitution, but we could also do row reduction on these matrices. But if you think about the process that you go through to do row reduction, it's going to end up being the same exact process, because we never make a decision on a row operation based on what's over here. We only make the decision based off of the coefficient matrix. The goal would be to turn that coefficient matrix into the identity matrix and then get something over here. But the operations we use to turn this into this are going to be the same in both cases. So what that means is, rather than solving them separately, we could augment them together, meaning take this and just slap it on right here and solve this augmented matrix. Now, another way to kind of interpret what I'm saying there is that to solve a system, you always try to get the identity matrix here on this side. So what we're doing is we're going to kind of ignore this. We'll keep track of the numbers that are here, but the goal is to get the identity matrix right here. Perform row operations until the identity is here rather than being over here. So let's try doing that. Okay, so I brought this to a new slide here. So we just want to perform row reduction on this augmented system till we get the identity matrix here in this place. The matrix that you will have over here will then represent our identity, or our inverse matrix, that is. Okay, so the first thing is we want a 1 to be in this position right here. Now, we could get that by just dividing this row in half, but we already have a 1 in this row, so to avoid fractions, at least at the moment, let's just switch the two rows. So we're going to take row 1 and swap it with row 2. Okay, so now in order to turn this into a 0, we're going to take -2 times row 1, add it to row 2, and that becomes the new row 2. So top row doesn't change. Then when you take -2 times this added to that, we get our 0 that we wanted. -2 times this, -2 times -1 is +2, added to this gives you a 6. -2 times 0, that's just a 0, so that's still a 1. And then -2 times this plus the 0 is going to give you a -2 in that spot. Okay, so first column is done. We have a 1 in the first spot, zeros are below it. Now move over to this column. We want the 6 to be a 1. We only have one option to get that. We're going to have to take 1/6 times row 2 becomes the new row 2. Top row is not going to change. Okay, divide this row by 6 here, so you get 1/6 and -1/3. All right, only one step left. We need to turn this into a 0. We can achieve that by just adding row 2 to row 1. So we have row 2 plus row 1 goes to row 1. All right, so that gives us 1, 0, 1/6. Then add the -1/3 to the 1, gives you a 2/3. And then the bottom row stays the same. So A inverse is just the square matrix that you see here. Now, if it truly is the identity matrix, then that means the product of this matrix with our original matrix A should be the identity. So let's verify that. Okay, so here we have the matrix A. Here we have the inverse that we just found. So we, to multiply them, take the first row times the first column. That is going to be 2/6 plus 4/6. Then let's move on to the next element right here, which would be the first row, second column. That's going to be 4/3 minus 4/3. Then go to the second row down here. Second row by first column is 1/6. 1 times a sixth plus, or minus in this case, -1 times 1/6 is minus 1/6. And then second row by second column is going to be 2/3 from the 1 times the 2/3, and then plus another 1/3. The negatives cancel here, so plus 1/3. All right, so that's just doing rows by columns for each of those elements. And then if you simplify them, you can see that's 6/6, which is 1. Those clearly cancel to give you a 0. These clearly cancel to give you 0, and that gives you 1. So yes, indeed, this was our inverse matrix. So the process that we went through there works in general. Again, that process is take the matrix, the coefficient matrix, the A that you have, and then put the corresponding identity matrix here. I should be pointing here. Put the corresponding identity matrix here. Perform row reduction until the identity matrix is on this side, and whatever is left over on this side will be your inverse matrix. So that's what it's saying here. If you want to find the inverse of a matrix A, then form the augmented matrix where you have A in the first spot and then the identity matrix on the right of it. Perform row reduction until you get the identity matrix here, and whatever is over here will be the inverse matrix. So let's try that again with a 3x3 this time. Okay, so I've put back in the matrix A, and over here I've put in this time the 3x3 identity matrix. So now we just do the same process, do row reduction until this is the identity. So first thing we're going to do is clear out the 2 and the 3 here. We will do -2 times row 1 plus row 2. That'll become the new row 2. We'll do -3 times row 1, and that'll become the new row 3. Take -3 times this, add it to row 3, becomes the new row 3. Okay, so let's do each of those. So top row is not going to change. Then -2 times this added to that gives us 0. -2 times 0 is still 0. Added to this keeps it as a -2. -2 times the 1 plus the -1 is -3. Negative 2 times that, negative 1 plus the 0 puts a negative 2 in that spot. Then the rest of these, you're going to multiply them by zeros, so they're not changing. That's going to be a 1 and a 0. Okay, now we take first row times negative 3, add it to the bottom row. So we'll get a 0 here. Nothing's going to change there. Negative 3 times 1 plus the 0 gives you negative 3. Then negative 3 times this added to the 0 puts a negative 3 there. And then nothing else changes. Okay, so we got what we wanted. We've cleared out the first column. Now we move on to the second column. There's only one thing we can do there. We need to multiply that entire row by a negative 1/2. We're trying to get a 1 in that spot there. So negative 1/2 times row 2 becomes the new row 2. Okay, so we've multiplied the entire row by negative 1/2. Okay, we can go ahead and take care of the last row as well. The goal with this one is we've already got the 0 here that we want. We need this to be a 1. So we're going to go ahead and take negative 1/3 times row 3, and that will become the new row 3. Okay, so now first and second column are finished, and we will want to use this one here to clear these two elements out. We want these to both become zeros. So we'll take negative 3/2 times row 3, add it to row 2, and that becomes the new row 2. We're also going to just take a negative times this row and add it to row 1 to clear that out. So we'll do negative row 3 plus row 1 becomes the new row 1. Let's actually go ahead and do this one first, so that since we're going to change that row anyway, so it's going to become 1, 0, 0. Negative 1 plus that gives you a 0 in that spot as well. The zeros aren't going to change here. Negative times this added to that puts a 1/3 there. So that's doing this operation on that top row. All right, second row. We have negative 3/2 times this one added to that puts a 0 here. Negative 3/2 added to this puts a negative 1/2 there. Then the 0 is not going to change that. That's still going to be a negative 1/2. And then you have negative 3/2 times this ends up being a positive 1/2. Added to this will be just a 1/2 there. And then the bottom row doesn't change. Okay, so this matrix that you see here at the end of this is our inverse matrix. So we can just rewrite it over here. And you can go back and double check. You can take this multiplied by the original matrix if you want to verify, but this is the correct inverse matrix. Okay, this next part that I'm going to cover in the notes is not something that you're going to see in the book. There may be some problems in the homework assignment that are related to this, but I wanted to explicitly go through this shortcut that we're going to go through to find the inverse of just a 2x2 matrix. We do enough inverses that I think this shortcut is actually pretty helpful. It doesn't work in general necessarily. You would need to generalize the result, but it works well for at least a 2x2 matrix. So here's our general 2x2 matrix, and we want to find the inverse of that 2x2 matrix. So if we go through that process that we did before, we would put the matrix A here, put the 2x2 identity matrix on this side, and then we would do row reduction. Now we're going to break this down a little bit differently. Remember that the where this came from was really two separate augmented matrices. So really you're solving the augmented matrix with this as the solutions, and then also the augmented matrix with this as the solutions. So I'm saying just suppose that this has the solution of x1, y1, and this one has a solution of x2, y2. Those solutions gave us the inverse matrix itself, written as columns. This would be the column matrix here, and this would be the column matrix here. So what we're going to do is we're going to actually solve these in general, and we're going to do that using Cramer's rule. So take that first augmented matrix that we had. if we're going to apply Cramer's rule to find the first x solution, x sub 1, we know that that's the determinant where we take the x column and we replace it with these numbers here. I just take this and we put it in place of that and do this determinant, and we divide it by the determinant of the coefficient matrix, just the determinant of this part here. Okay, so I've just written what this determinant would look like, put this in this column here, and then to do the determinant, you multiply the diagonal terms first, 1 times d minus 0 times b. Well, the only thing that's going to survive that is the d. And then we're divided by capital D, the determinant of the coefficient matrix. We're not going to write that out for now because you'll see it's going to show up on all of them. Okay, so to get the y solution, do the same thing. Do the determinant with the y column replaced by these two numbers, divided by the determinant of the coefficient matrix. So this determinant here, a times 0, that gets wiped out, minus 1 times c, which is just a negative c. So these two represent your solution for x1, y1, which means they go in these two spots. They fill in the first column. So the first column of the inverse is d, little d, over the determinant of the coefficient matrix, and then negative c over the determinant of the coefficient matrix. We then do the same exact procedure with the other augmented matrix, where its column is a 0 and a 1. And you can see their solutions are negative b over d and a over d. So every single one of these has a d in the denominator. Now what that means is we can actually pull that out using scalar multiplication. I could just write it as a 1 over d multiplied by the matrix that just has the numerators in there, which you get here. And remember here, this d is just the determinant of a. If you wanted to, you could write it all the way out. This would be a times d minus b times c. That is what that determinant is, but I'm probably just going to leave it like that, then put the rest of it in here. And then let's look at what's actually happening here. So if we go back to the original coefficient matrix, what changed is we swapped this diagonal. The a and the d were swapped, and then the b and the c have negatives on them. So in general, all we will need to do to find the determinant of a 2 by 2 matrix is swap the elements on the first diagonal, take negatives of the elements on the second diagonal, and then multiply by 1 over the determinant of that matrix. Okay, so let's go back and apply that to the first matrix that we found an inverse of, this 2 by 2 matrix here. So according to this shortcut, the inverse should be equal to 1 over the determinant of this matrix. So that determinant is going to be 2 times negative 1, which is negative 2, minus 4 times 1, which is 4, multiplied by, now on the inside we need to flip this diagonal, so negative 1 here, 2 here, and then this diagonal doesn't flip, but we do put in minus signs, so negative 4 and negative 1. Then we just simplify this, so this is really negative 1/6 multiplied by this matrix, and then distribute that through the matrix, so you end up with 1/6, then positive 4/6, 1/6, and 2/6. And then if you have any fractions that can be reduced, go ahead and just reduce them. So 1/6, 2/3, 1/6, and lost a minus sign. This should have been negative here, right? Negative 1/6 times the 2 should have been negative 2/6. All right, there you go. And that should match the inverse that we found earlier. Definitely a lot easier, but again, the drawback here is this only works in a 2 by 2 matrix. But it does illustrate something that is true in general. If the determinant of the matrix is 0, then you're going to have 1 over 0 here, which is undefined. So when that happens, whenever the determinant is 0, there will not be an inverse matrix. So you can actually see that in this example here. So this says identifying a matrix that has no inverse. So if we were going to try to do that same procedure, the very first thing we would need to do is the determinant of matrix A, which in this case would be 2 times negative 2, so negative 4, minus 1 times negative 4, which comes out to negative 4 plus 4, which is 0. So this is going to cause a problem because according to what we said before, the inverse should be 1 over that determinant multiplied by, then you would flip these two, so it would be -2 here and a 2 here, and then you'd take negatives of those, so that would be a 4 and a -1. But you're not going to be able to do that because you have division by 0. So for this, we would just say it does not exist. There is no inverse to that matrix. Now, if you don't want to do it using this method, or let's say your matrix is not just a 2 by 2, then the other method will show the same result. The original method, I should say. So that original method was to start by writing this matrix out. So 2, -4, 1, -2, and then you put the identity here. And then you do row reduction. So for this one, I'm going to go ahead and just multiply the top row by 1/2. And that just becomes the new row 1. So that's going to put 1, -2, 1/2, 1, -2, 0, and 0, 1. Okay, so all I did was multiply the top row by 1/2. Now, if we take negative row 1 and add it to row 2 and make that the new row 2, we end up with top row stays the same, but then the bottom row, these are all going to get canceled. Over here, you're going to get a -1/2, and then here you're going to just get still a 1 there. So this is a problem because really there's two systems here. We're really saying two different things. We're saying 0x plus 0y is equal to -1/2, but we're also saying that 0x plus 0y is equal to 1. Either one of these is a problem because this really says that 0 equals -1/2, which can't be true, and this one says 0 is equal to 1, and that can't be true. So if you end up with a row of zeros here, you know that there is no identity matrix, or sorry, no inverse matrix. Remember, the goal was to turn this into the identity, and if you can't do that, if you can't make this the identity matrix, then there is no inverse. So that's the other way to see that you have no inverses. Perform this row reduction. If you don't get the identity over here because you get a row of zeros, then no inverse. So not every matrix, not every square matrix has an inverse. Okay, so how are inverse matrices useful to us? Well, they have many uses, but for us, the one we're going to look at is that we can use them to solve a system of equations. So here is a general 3 by 3 system, meaning 3 equations with 3 unknowns, x, y, and z. This system can be represented using matrix multiplication. So the way we break it down is we're going to define matrix A to be the coefficients of all of these in all of these equations. So this is the coefficients from the first row, second row, and then the third row. We're going to define this column matrix X, that's a capital X, to be just the variables, the unknowns, x, y, and z in this case. And then we're going to define the matrix B to be the constants. So these are the column matrix that just represent the constants. This system can be represented as matrix A times matrix X equals matrix B. So let's take a closer look at why that is actually what that system is. So if you, actually I think I want to keep it there where you can see all of it. Okay, so if we take matrix A and we multiply it by matrix X, then the rule for that is it's the rows by the columns. So also notice that the dimensions here, this is a 3 by 3, this is a 3 by 1. So when you multiply them, you're going to get a 3 by 1, meaning a column matrix, 3 rows, 1 column. So the column, the first element I should say, is this row by this column. So you just get A11 times X, A12 times Y, A13 times Z, add those together. Move on to the next row. This row by this column gives you this element. And then this row by this column gives you this element here, this sum. Well, those are exactly what you see over here. That's the first element here, second, third, right there. So matrix A times matrix X gives you exactly what this is. And these expressions, these three expressions here, are supposed to be equal to b1, b2, and b3 respectively, according to this. So this is exactly AX equals the matrix B. So that's why I'm saying that a system can always be represented as a product of matrices. Okay, well, let's say you wanted to solve this equation with numbers. Let's say it's not matrices, it's just numbers. Then how would you do that? Well, you'd want to get rid of this A. If you want to solve for X, you want to get rid of A. How do we get rid of A? You're probably thinking, well, you divide both sides by it. Yes, true, but another way to do it would be to multiply by the multiplicative inverse, meaning that we could multiply both sides by 1 over A. So then the idea is, using the associative property, you could go ahead and multiply the 1 over A by the A. This would just be 1. They would just cancel out, so you would get X equals 1 over A times B. But remember, 1 over A could be written as A inverse. So this is one way of representing how we would solve that equation if it were numbers. It turns out this also works for matrices. The exact same procedure. Start off with thinking of these as matrices now, not as numbers. So we've got matrix A times matrix X equals matrix B. We're going to multiply the left-hand side of each of those expressions by the inverse of matrix A, assuming that inverse exists. So just multiplied by the same thing on both sides. Using the associative property, we can group these two together first. And then if we form the product of A inverse times A, that is just the identity matrix. It's what it means to be inverse. So you just get the identity here. But the identity times any matrix is just itself. So the left-hand side just turns out to be just matrix X. And the right-hand side is what we had before, A inverse times B. So if we break this back down, matrix X was just the column matrix with the variables in it. And then this product would be whatever matrix A is times the constants. So if you form that product, it will give you a column matrix that will tell you what X, Y, and Z are all equal to. So let's give that a try. Let's start with a 2 by 2 system. So in this case, the coefficient matrix is the matrix 2, -3, 1, 5. The variables, matrix X, and this is a capital X, would just be X and Y. And then the constant matrix, the B matrix, would be 4, 2. Now, according to what we just wrote, the solution, which is this matrix here, X, should be A inverse multiplied by B. So we need to figure out A inverse. Well, it's a 2 by 2 matrix, so we can use our shortcut. We know that it's 1 over the determinant of this matrix, so that would be 10 plus 3 there. 5 times the 2 minus 1 times the 3, multiplied by, then the matrix inside here, we have to flip these two, so 5 here, 2 here. These do not flip, but they change signs, so 3, -1. All right, so this is really 1 over 13 times that matrix. Now, you could distribute this through, but I find it actually easier to just leave it like this. So if we go to what it says up here, our solution, in other words, xy, is supposed to be equal to A inverse times the B matrix. In other words, it's this. It's 1 over 13 times this matrix. That is just A inverse. This whole thing is A inverse times B. Okay, so again, the 1 over 13 could be put in here. You could divide each of those by 13, or we could just wait until the end and divide by the 13 at the end, which I find to be easier. So we're going to leave this 1 over 13 out here. Go ahead and multiply these two matrices. So it will be a column matrix. The first element is going to be 5 times 4, which is 20, plus 3 times 2, which is 6. And then the element down here is going to be 1 times 4 is -4, plus 2 times 2, so plus 4 there. So that is 1 over 13 times 26 and then 0 in that spot. So just distribute this through and you end up with 2, 0. In other words, the solution for that system is x is equal to 2, y is equal to 0. So we now have at least 3 ways of solving a system. The original way was row reduction. Just perform row reduction to solve the system. Write this in augmented form, row reduce until you get the solutions. We learned Cramer's rule, and now we have a third rule, which is find the inverse of the coefficient matrix, multiply it by the constant matrix, and that product will be equal to your solution. Now, one thing I should have pointed out earlier is this solution method only works if the coefficient matrix is a square matrix, which means this method, the method solving the system like this, only works when you have the same number of equations as you have unknowns, which is the most common case for us. But let's try it once more with a bigger matrix. So first thing we need to do is write down matrix A. So matrix A is going to be 1, 0, 1. Okay, remember it's just the coefficients, so I'm getting that from this right here. 1 from the coefficient of the x, 0 is coefficient of the y, 1 is coefficient of the z, then 2, -2, -1, 3, 0, 0. So that's our A. The matrix X is just all the unknowns. And then matrix B is the column matrix with the constants. So -1, 5, 6. Okay. So we need the inverse of this. Well, lucky for us, we actually did the inverse back in example 2, I believe. So we've already found this inverse matrix, so we'll just copy it back down here. All right, and so then to find the solution, we know that x is equal to A inverse multiplied by B. So we just need to take this matrix, multiply it by that matrix, and we have solved the system. So there's A inverse multiplied by B. Okay, so when we do this product, again, it's going to give us just a column matrix, so it's row by column. So the first one, you've got 0 times -1, 0 times 5, and then 6 times 1/3. That's the only thing that lasts, is the 6 times 1/3, which just gives us a 2 in that spot. Then we have a 1/2 minus 5 halves, then plus 6/2. So that's coming from taking this row times this column. -1/2 times -1 is 1/2. -1/2 times 5 is the -5 halves. 1/2 times the 6 is 6 halves. We'll simplify that in a second. And then final row times that column is -1. The 0 doesn't do anything. And then it'll be a -1/3 times the 6. So that's -2. All right, so if we simplify this, top one's already done, that's 2. This, if we add that together, we're going to have, looks like we've got 7 halves minus 5 halves, which gives us 2 halves or just 1, and then -3 here. So then that is our solution. In other words, x is equal to 2, y is equal to 1, and z is equal to -3. And that's it. So again, it would have been, this looks really easy because we already had the inverse. All the work was wrapped up in just finding the inverse matrix. Now, out of all the methods, is this the first one you should choose? Probably not, but the biggest benefit of this method is, suppose you had a certain system that you had to solve multiple times where the coefficient part, meaning all of this stuff over here, did not change, but these numbers changed. Let's say we had to swap these out for 3, 7, and -8. Well, the benefit of this method is you still solve it the same way. You would just need to change that matrix into 3, 7, 8. You could just multiply this inverse times that column, sorry, -8, multiply this inverse by this column matrix, and you would have solved the system. And then if you needed to, and you needed to change the numbers again, you could just update them again, and again take the inverse times the new updated column matrix. So it would enable you to resolve a given coefficient matrix solution very quickly. Before you go, I did want to show you that your calculator can do this as well. Okay, so you can enter your matrix in any method that you like. So I've just stored the matrix as A. This is the exact same coefficient matrix, I believe, that you see right here. So to find the inverse of it, we need to recall the matrix. So just go back to second matrix, hit enter on it, and then it's as easy as just using the reciprocal button. So it will actually interpret this as a matrix inverse. If you hit enter on that, you're going to get it with decimals, but if you go to math and use convert to fraction, it'll take that matrix and spit it back out with fractions inside, as long as they're not too nasty for it to convert. So that makes it very easy to find an inverse of a matrix. And then you can also do the matrix multiplication on here as well. If we take that and we multiply it by, let's put in a new matrix here. So we need a 3 by 1. Okay, so it's taking this matrix, which is the answer. We're going to put in those constants there, so -1, 5, and 6. So that's A inverse times B, and you can see it gives us the answers there. So yes, you want to try to practice doing this by hand, but once you get the idea, you can use the calculator to speed up the process as well. Okay, so I think that takes us to the end of this section. Hopefully this is helpful. If you have any issues with the homework, make sure you're emailing me, and we'll see you guys in the next video.